Assalamu alaikum and hello everyone. I welcome you all in today's webinar on designing building systems in ETABS and concepts. For today's session, our resource person is engineer Zishan Ahmed, who has a vast experience of more than 14 years in the construction industry. He is a civil structural engineer who is currently pursuing his PhD in structural engineering. Without any further delay, I would like to invite Engineer Zishan Ahmed to start his webinar.
Hello, Assalamu alaikum. Welcome you all. Good evening, everyone. Welcome to the webinar. My name is Engineer Zishan Ahmed, and I will be delivering today's session. This is regarding the ETABS and the structural engineering concepts. So let us start the session. A civil engineering structure is a combination of different members. The main function of a building is to support the loads and to make it safe enough to bear all the loads there. It may be the gravity loads or the lateral loads. And the primary function is to support and transmit the loads safely to the foundation. The load patterns, as you know, that gravitational loads, the loads are transferred from the roofs to the beams, to the beams to the columns, and from columns to the foundation. But in reality, we could not have a simple structure. We could have unsymmetrical building also, like this one, or this one. So what we have to do is to accurately design. Normally, there is a debate. Some people say, or some engineers say, that softwares are not that reliable, and you have to do it the manual way. But it's not that way. In manual designing, you only design for gravity load. We take the help of the software because software optimizes your work, and if you don't use the software, if you are designing a 50 plus building, so you will take months to design it. By the aid of the software, it only takes a few days. But pure rely on the software is not basic concepts and the basic checks to know that whether your design is safe or not, because software is just like a machine. Whatever you give the input, it will give you the output. But if you have not given the proper input, the output will not be proper. So you have to have the checks to check whether the values are not drastic. For example, if you design a beam of 40 inch, so that can be designed by software, but is it practically acceptable? So that needs to be checked. And basically, we should always try that as we go from top to bottom, the area should be increasing, not decreasing. It should not be like this. It should always be like this, right? As we go from top to bottom, the yeah, base should be widen enough to support the loads. You can see here, this is a convex arrangement. Normally, this should be the recommended way of designing, not this one. If you go for this one, so it will not be safe enough, right? So, in addition to that, you could be having different types of uh, array shapes. For example, you could have like this, or a complex shape like this, L shape, T shape, U shape, V shape, X shape, Y shape. So what is the main difference in designing these? The torsion and the twisting effect comes into play. So for that, the design gets a little more conservative, and you have to do proper checks. These are the section views of a building. You can see here that this is a building which has a floors and the columns, the footings, and this is a flat slab arrangement. You can see the drop panels, you can see the basement walls, the pedestals, the column capitals, the flat slab, the flat plate, and the interior columns. So this is a typical building section view that we normally see in our engineering field. So There is always a conflict between architect and a structural engineer. Architect mostly look for the aesthetics and doesn't have much knowledge about the structural stability, whereas as an engineer is always concerned about the structural stability and its performance. So they both have to work as a team in order to make it structurally sustainable as well as aesthetically good. But safety is the main concern. You should not compromise the strength with respect to the beautification. So that debate needs to be resolved. And for a bridge structure, an engineer is also always the architect, because in bridge we do not have architects. So bridge aesthetics is always dependent on an engineer. The structural systems, we could have gravity load systems, right? And the lateral load resisting systems. In gravity systems, we can have this slab supported on load bearing walls, slab supported columns, slab supported on beams, the beams supported on another beams. What happens is that if the spans are long enough, so if you can see, these are spans. For example, this is a uh, these are two beams resting, so we have to provide an internal beam in order to control the deflection and also the depth of the beam. So this beams is thus resting on the another beam, not on column. So in that case, the we give the what we call as the hinge, or we can say that the moment releases. Since the beams are resting as a simply supported, so the joints are not rigid there, and that is properly modeled in the software like the ETABS and SAFE. When we have secondary beams, the options are there, and then we manually give the input as secondary beams and primary beams. And lateral load resistance system, which we can have single system, the moment resisting frames, the bridge frames, the shear walls, and tubular systems and a dual system. As we move down, the height increases. So as we go higher, then we go with the advanced shapes, and performance-based designs comes into play. So what is a wall bearing system? These are typical G+2 type of buildings maximum, which the slab is supported directly on the columns, and the columns may be of bricks. And there is no proper design. These are all basically thumb rules and old standards. But these, keep in mind that these are not seismically strong enough, and for high seismic zones, they are not recommended. So we have to avoid, even if you are providing a G+1 building. So in high seismic zone, you have to avoid this, because they have no lateral resistance, and only gravity load it is supporting. So in that case, if lateral load acts on it, the building is likely to collapse, and you can have the loss of life. So moment resisting frames is a combination of beams and columns. You can see in this image that there is slabs. Slabs are supported by beams. Beams are columns, and from columns down to the foundation. A frame may be composed of a strong column and weak beam system, or a weak column and a strong beam system. But naturally, we go for strong columns, because the columns are the main supporting elements, and you have to give the column more strength than the beams. If beams are stronger, then all the torsion will be taken by the beams, and the column will not take torsion. In case of lateral load, it is vulnerable to not behave properly. Okay. And they are mostly used for medium rise buildings. For example, you can go up to maximum G+10. Okay, shear wall. When the height increases, or we have non-symmetrical shape, like we have this type of arrangement, or you can say that this type and this type of arrangement. Okay. So in that case, the twisting effect comes into play. We perform the modal analysis in this type of structures, And in model analysis from the results, we give different modes, and we have to control the translation as well as rotation. So if that is not controlled, and as per the code there are some values, some code says that 90%, and these are basically ux, uy, and uz, and rx, ry, rz. So the software performs these analysis, and they give the result. You have to check whether these are as per the code satisfying or not. If it is not satisfying, then you go for the walls. Basically, the purpose of the wall is to give stiffness to your building. As you go high, the stiffness reduces. So in that case, you have to stiffen the building, and this is the best option we have. And you can use in moment resisting frames also. As we go higher, then the demand of RCC walls increases, right? Okay, brace frames, as we go higher from a particular story height, then moment resisting frames are not safe enough to be used in the design. So in that case, we use the brace frames. The frames could be diagonal frames, it could be X frames, V frame, chevron bracing, K bracing, and global bracing. What is interesting in this is that it also gives you good aesthetic view, if you can see from the outside in this image. So not only it is performing structurally safe, but also it is looking and very good as aesthetic view. So it is serving purpose for both the designer and architect. Normally you can see nowadays that some buildings are like very awkward designs. You can see the cross bracings and the non-vertical members. So this is because of all of these are because possible because of this performance-based design. And when you have the design adequate, you can provide any shape then, right? So the types of building based on stories, if you call mid-rise buildings up to G+10, you can go for mid-rise buildings. Up to G+20, they can be called as high-rise buildings, and tall buildings G+100, and so on. There is no limit. And nowadays, you must have heard that in Abu Dhabi they are building building which will have a height of 1 kilometer. So even that is also possible. There is some interesting facts about this mid-rise buildings and the short building and the tall building. I will explain a bit in detail this. For example, these are 3 buildings. For example, this is short building, and these are medium building, and this is high-rise building. And if you give earthquake to it for low frequency, this high rise will be at low frequency, this will oscillate, but at medium frequency, medium rise building will oscillate, and for high frequency, this short building will oscillate. What we have seen recently at the very strong earthquake at Turkey, that most of the buildings were medium rise, mid rise buildings, and they collapsed because the P delta effect was not considered in the design. There are 3 important things you have to know. One is the P delta analysis, and the buckling, and the residual strength. What happened is that a very strong earthquake of 7.8 magnitude, followed by an aftershocks of 7.6 came. The buildings that survived the first shock were not able to survive the second shock because it has already lost its strength. So as we go high, we don't go with the linear analysis. For example, if this is a building, the higher you go, the sway will be getting increased. So in that case, if it is a linear shape building, so it will be too high and the columns are likely to buckle. So in that case, we go with the non-linear analysis, and for that, the dynamic analysis comes into play to make the curve from first degree to second degree to comes into play the hinge effect and the performance of the frame member in elastic range. So, rise building operation. Kindly mute if you have some question. Okay, so high-rise buildings, we can have the brace frame, the tubular structures, and the brace tube structures. And if you go see on the right, as we increase the number of stories, the building configuration changes. You can see here, the type 1 is the shear frames, type 2 is the interactive systems, type 3 is the partial tubular systems, and type 4 the tubular systems. So we can see that the center core arrangement, and these are all you can say shear wall type of arrangement, and the purpose is to give stiffness and uniformity. It is provided in the center to give more stability in the building, right? So as we go high, we can have any type of arrangement, but tubular structures and the diagram arrangements are normally used in the high-rise buildings. So the deformation capability of the buildings, if you have a moment frame only, as we go high, the sway effect is getting increased. So we provide the structural wall, but structural wall also, if you can see, it has also, as we go high, the drifts are exceeding. So when we go with the global brace, you can see that the drifts are reducing. So that is the recommended solution for high-rise buildings. The more you go high, you have to use the bracings also. And in buildings, as we increase the number of stories, the second order P delta effects comes into play. You can see for a 5-story, there is no appreciable drift. In 10 stories, the drift is coming into play. 15 stories, the drift is increasing, and in 20s, it is more increasing, and in 25, it is going to an unacceptable limit, which causes the damage to the building and non-performing in case of an earthquake. So based on the number of stories, what we can classify as up to 60 story, you can go with the concrete frame tube, up to 80 story steel frame tube, and also tube. For example, this is the internal core arrangement, and higher 100 stories concrete brace tube. And as we go high, the number of floors are getting increased, so we go with the space truss and super frame arrangement, right? This is just for description. Okay. So what are the different methods of structural design? You can have the working stress method, the ultimate strength method, and performance method. Working stress method is now non-popular because it is not as per the latest design codes. The ultimate strength method, the LRFD method, is used for a particular height. Movement resisting frames are using it. The performance-based design is the most used for high-rise buildings. The higher stories all are designed based on the performance base. So what we have to do is the serviceability design. You have to have the allowable material and control on the deformation limits for design load. In strength design, the material failure criteria comes into play. The section capacity is designed for the factor loads. In performance design, you have to have a ductile structure and not a brittle structure, and the deformation capability is increased, and the loads, extraordinary loads are considered. So it is basically the performance, and based on the performance, you design your structure. For example, if you are designing a moment resisting frame, so you know what type of building you have, but in performance-based design, you cannot restrict yourself to any type of building, because based on the performance, you will then decide which type of building to be used. So what happens in the building, what is the load distribution arrangement, the gravity loads, they are transferred to the vertical members, and some terms that are used in software. Software classify these as diaphragms, the slabs, then the movement resistive frames, and the shear walls are also there. So what shear wall does, it transfers the lateral load to the vertical members. So you can see that the lateral load, as we go from top to bottom, the intensity reduces, but the drifts are excessive at the top floor and less at the ground floor. Right. So we know that major elements in a building frame structure are the load bearing and non-load bearing, the beams, columns, slab and footings, and non-load bearing, the claddings, the partitions, the ceilings. What happens is that under excessive earthquake, the non-load bearing members, they tend to fail, and these can also cause major casualties, and that's because the building is stable enough, but due to these falling of these non-structural elements which are not normally designed, nowadays research is going on to also design the non-load bearings, because they are also vulnerable and are a safety concern. So the loads and the buildings are the dead loads, the live loads, the hydrostatic and soil loads, and the snow loads. All these comes under the static loads. And dynamic loads, you have the wind loads and the seismic loads. What is the basic behavior? The vertical, the gravity load, it causes this kind of creates this kind of elastic curve, and lateral load, it forms this kind of elastic curve. So in lateral load, the buckling is the major concern, because under too excessive drifts, the column tends to buckle, and as it buckles, the it gets failed, and due to the failure of the column, the entire structure is prone to fail. So now comes a very important thing. This soft story effect. This is the major point of discussion nowadays after the earthquake of Turkey. What happens is that in plazas you have seen that the basement is reserved for parking. So due to the parking, the spaces are open, and open spaces causes this soft story. By code, what is meant by soft story? Soft story is one in which the lateral stiffness is less than 70% of that in the story above, or less than 80% of the average stiffness of three above stories, right? So the base structure, the base stories always have low stiffness because of these open spaces. So what happens that under earthquake, this soft story effects comes into play. The plastic hinges tend to form, and due to this plastic hinge, the column tend to leave its position, and it causes the collapse of the building. This is what has happened recently. If you have seen the visuals of the earthquake, this is what has happened. What's ultimately happens that the building falls down, right? First the vertical members fails, and then the building falls down. So how can you minimize these soft story? By providing the shear walls, the bracing, or the steel framing arrangement. So weak story effect, this as per the ACI, you have to check the vertical irregularity also. It is mentioned that a structure is classified as weak story if the shear strength of the story is less than the 80% of the shear strength of the story above it. And also extreme weak story exists if the shear strength of story is less than 65% of the shear strength of the story above. These are taken from the code. So these checks are also performed before designing a structure. And all these are not recommended because it causes the damage to the structure. So in foundation design, one is the superstructure, and the superstructure is supported on the substructure. Foundation is that part which is in direct contact with the ground. You have to place your foundation in such a way that it is safe enough, and it is not having any moisture or the passage of water. So it should always be dry, because what happens is if you have a saturated clay type of soil, due to saturation, the liquefaction effect comes into play. and due to liquefaction when the lateral load comes into play. So it causes loss of shear strength of soil. We need to say that the shear strength gets zero. Due to zero shear strength, it acts like a flowing water and it collapses. So importance of a proper foundation is very important. You as a structural engineer, you always have to see for a mega projects, the soil investigation report is very must. Normally, it is the geotechnical engineer who recommends the type of foundation. It is his duty to give you recommendation what type of foundation you have to design for small projects or for projects in safe zones. You can do it by yourself also, but for that you also need the soil investigation report. Without this, if you go on designing, it might not be acceptable in the latest stage of building performance. During earthquake, the vulnerability might come into play. So a foundation is very important, and if you have a building where the water table is very near, so you cannot place a foundation there. You have to go with the deep foundation. Then you have to go. You can go with the piles, or you can go with the soil stabilization. So this is very important, and it comes from experience. Always the design should be vetted before implementation. So, what is a shallow foundation and what is a deep foundation? The shallow foundation in which the width is greater than the depth of the excavation, or the depth in which the soil is placed, the foundation is placed. So that is classified as the shallow foundations. Okay, we will now discuss the type of shallow foundations. We can have the isolated footings, the like this, the strip footings, the raft footing, and for if you have a slopy ground, the step footing also, right? So what is a deep foundation in which the depth is greater than the width? So that is called as a deep foundation. And there are certain requirements why we go for deep foundation. So the foundation selection based on the soil conditions, the soil close to the surface should be capable of supporting the loads. You can go with the shallow foundation. The soil in which the hard strata is found very deep, as I discussed, for example, this kind of slopy ground, which the hard strata lies very below. So you have to go with the deep foundation. And ground having differential settlement, you can go with the raw foundation. And if the ground is not level, you can go with the step foundation, right? So now coming to the modeling of soil in software, the FEA softwares like ETABS and SAFE, they model the soil. When we have point spring. The point spring is used when we have a pile foundation. When you have a pile foundation, then the soil is modeled as a point spring. And when you have the isolated footing or raft footing, then it is modeled as area spring. And when we have strap beams, then it is modeled as line spring. All these are modeled in the software, and these names are used there. So this is just for your understanding that how we model the soil in softwares. Now coming to the ETABS, ETABS have this interface when we open. This is a screenshot taken from a 2015 version. So when we open, we have the units at the bottom. Always check your units, and then we have the coordinate systems. There we can see the one story. It means that if we select any member, only that story will be selected. But if it is selected as all stories, then if we click on one member, all the, for example, if this is a frame and you click on this beam, and it is selected as all. So all the beams, they will be selected, right? So this is always checked by assigning any member or any property. We use this check to see whether we are selecting one members or only. If you open ETABS, you will see by default this type of three windows. In this view, you can see the plan view, and this you can see the 3D view. You can always change the screens by yourself. You can go with the single screen also from this button. If you click in the here and you click on this 3D, the 3D view will come into play. If you click on the plan you will be seen, and if you click on the elevation views will come. These are the toolbars, the menu bar. You can see these are the shortcut keys, and this is the vertical toolbar. You can see the different shortcuts here. Here we see this is the button for slabs. This is for frame members. It can be beam column, and these are for walls, right? So these button we use the most. These are for the different options we use. For example, the viewing options. And when we analyze the model in ETABS, this button, the model is then locked, and this is the button used for the run analysis. By this, you can increase the zoom view or decrease the zoom view, and you can go closer to the model, and you can go farther from here. And these are the buttons used for assigning the loads, and this is for undeformed shaped. So these are some important interface buttons I have taken from the screenshot. Next, we will discuss the different abbreviation in ETABS. So how we design the building in ETABS. So first we define the geometry of the building. It can be in the shape of grids. Normally, the FEA is based on the finite element method. It performs the discrete analysis. It divides the member into small components, and each member has different nodes, and it is connected by nodes from one member to another. So you can, by default, go with the grid option, or you can also model the structure by importing the file from AutoCAD or even the Revit. In that we use the import DXF file option, right? A file already prepared in AutoCAD or Revit, it is then imported in ETABS, and modeling is done, right? If you are not using this option, you can manually model it also in ETABS. So the first step is the defining the grids and the number of stories and their properties. The second step is then we define the materials, the steel, the concrete. We give the different strength to it, and that strength we then use in the design. So if our design is not satisfying, then we can go back and change the values, just like we do it manually. When our design is not satisfying, we change the values and the properties. Then we go over the design section of members. It can be beams or columns. So then we do the first we assign the frame members, the beams and the columns, give the different sizes. Always we use trial sizes. For example, if a requirement is beams of 12-inch by 15-inch, so we give multiple options like 12-inch by 15, 12-inch by 18, right? So what happens is that when we analyze and if it is not satisfying, then we only have to change the properties. Otherwise, you have to again do it manually. So it is always better to give multiple sizes and check if it is performing or not. So after assigning the beam, columns, slabs, and the walls, we then go with the drawing of the members. We draw the members. There are, as I explained in the previous slide, the buttons are used. We place the columns at their location. We place the beam at their location, right? And we place the slab at their location. And if we have a shear wall, we place it at their location. So all is done, and the model comes in this kind of a shape. This is what we get then after modeling the beams and columns. What we do then, we define the load cases. As per code, the ETABS has built in the different codes, the American codes, the Indian codes, the Chinese codes, different codes, European code. Based on that, it gives you automatic load combinations, and you can modify the load combination as per your requirement also. So by that, we give the properties and the loads. And the self-weight ETABS automatically calculated for automatically it calculates self-weight, but in StatPro software, self-weight is manually assigned, but in ETABS and safe or SAP, self-weight is automatically calculated by software, right? Need to assign a self-weight. We only need to assign the superimposed dead load, like the finishes, the partition load, the wall load. We have to only assign that. What happens then? Then we, after these steps, we then go with the assignment of properties. We give different properties to the column, beams, slabs, and the type of support. It can be hinge support, fixed support, roller support. So after that, what we do, we perform the analysis. We can have elastic analysis also without a P delta and inelastic. For a complex building, high-rise building, you have to perform the P delta analysis and not the elastic range. Okay, so after that, we perform the static analysis or the dynamic analysis, like that. In the dynamic analysis, we go for the time history analysis also. After that, we run the analysis, and the building give us this kind of shape. These are the color combination, and if we click on any member, it gives the property, the bending moment, the loads coming, and these color basically gives the zones which are critical and which are not critical. So these are taken from there, and from that we go with the design, and this is one of the image from output. And if the member is passing, if the member is passing by default, it is giving us a purple color. Purple color. Not passing, it will give us red color. In that case, we have to select it and check why is not passing, and we then go with the reanalysis and redesign of it, right? So what happens then, that we design, and we design for steel, concrete members, the component section can also be designed, and the connections can also be designed. And in the end, we get the project report and the detailed report. Okay. So, what ETABS give us after analysis, we get this reaction forces, the shear force and bending moments diagram, and the axial force diagram. All these are performed by software, and you can visually check each member and see for yourself whether they are satisfying your requirement or not. Some notations that important in the ETABS in by analysis and design. What we see that P is the axial force, V2, there are V2 and V3 shear force operations used in the ETABS. So we will, this is the V2 is the primary shear force, so we will take this value and not the V3, right? And T is that exit torque about one axis, and the principal bending moment is the M33 and not M22. So always take the values of M33 and V2. These are the shear values, shear force, and these are the bending moments. So if you have to manually check, you have to take these two values and check your design accordingly. Okay. What it happens that this is the V2 and this is the M3 and this is their behavior. Okay, so are the checks we perform after analysis. We don't straight away go with the design. If you go with the design, software will design for you, but this will not be. Screen is sharing, everyone, you can see my screen. Okay. So drift is the maximum lateral displacement. You have to check this. Some issue, I think. Okay, so drift is the maximum lateral displacement, and story drift is the lateral displacement of one level relative to another level or below. So we always need the maximum displacement of that particular story and also the adjacent stories above and below the above in those stories. So story drift ratio is the story drift divided by the story height. What happens that is the D1 is the drift at floor 19 and D2 is a drift at floor 18. So what will be the story drift? It will be D1 minus D2. So the story drift will be 6.01 millimeter. So that also keep in mind, not go with this value that this is the drift. It is always a difference between the two stories, right? Okay, what is the torsion irregularity? What happens is that in unsymmetrical building, the center of mass and center of rigidity, they don't coincide. So when they don't coincide, then twisting effects comes into play, right? So the torsion effect then comes into play, and how can we control it if we have, for example, this type of building, and we have a column of, for example, by 12 by or 18 by 12 inch. So the larger face should be always in the longer dimension, right? So this will help in controlling the this twisting effect. What happens is that the gap then reduces. If you increase the stiffness in one direction, the gap reduces. And another arrangement, you can go with the shear wall, and this is a trial and error method. We do it different trials, and ultimately we reach a stage when the iteration is successful and we control these torsion irregularity. By the code, what is meant by torsion irregularity? The D maximum, the maximum drift divided by the average drift, it should not be greater than 1.2. The software automatically calculates these values for you. Only you need to have to check the ratios. And what is the extreme torsion irregularity? When this ratio is greater than 1.4, then we call it as extreme torsion irregularity. So in no case we should allow the irregularity to take place. So these three important checks along with the drift, you have to check after analysis, and then if it is okay, then go with the design, right? So these are some aids from the codes. Um, what the codes gives us, and we then put it in the software. For columns, they give the moment of inertia as zero point 0.7. For the walls uncracked as zero point 0.7. For cracked 0.35. For beams 0.35. And flat plate and flat slabs, they give us 0.25. These are basically called as the modifiers, and modifiers we manually enter during modeling, right? So a type of member if you have, so based on that, from this code you can take and place in the software. So how is slab calculated? This also from ACA code. If you have different strengths and different arrangement with without H beam, with H beam, interior panels, with drop panels, you can use help of this, and by manually calculating, you can place the values in the software and check whether it is satisfying or not. Similarly, for the depth of beams, this is also from the ACI code, and these are different types of arrangements. The simply supported and continuous, both and continuous and the cantilever. After analysis, we check the long-term deflection. The members, we manually check on it, and we see the values. If it is less than this, it is okay. If it is more than this, then it is not okay, and we need to modify our modeling and then reanalyze our software analysis. So what is the one story, as I already explained. One story, if you see here in the bottom of that ETABS. So one story is one which you select and only one member is selected. All stories is one in which all stories are selected. And similar story is one if you have two floors similar. So we assign the property of similar. So in that, if you click on this one member and the other is similar to it, it is also selected. So in that case, similar stories also used. So all these helps us in saving our time, right? So units always important to check the units before modeling, and there are two units types: the use defaults or the metric. So you have to use both of them. The modulus of elasticity, this value is also manually calculated, and if you are having a 3000 psi concrete strength, so you use this formula and put this value manually in the software, right? This is for this kind of unit weight, and for normal weight, this kind of this formula is used. So these are something which we manually calculate and then put in the software. So this is from the Building Code of Pakistan, the previous version. For bearing wall systems, we have these values of R. For the building frame system, the values of R, and the moment resistive frame, the dual system, all are given for different zone also. So we take help of these and then enter it in the software. And the importance factor, this is also using the software, and these are the different description, what type of building you are designing, and from this you can take the values. And these are the floor loads. These are also manually entered in the software. For example, if you are designing a hospital, so for hospital, the load PSF is given. For library is also given. The residential also given. So assembly is also given. So take help of these and then put it in the software. So some other important modeling for slabs. We use the thin shell element, the thick shell element, and the membrane. So these are all explained here. You can see that the thin shell element it allows in and out of place stiffness. The thick it also have the deformation, and the membrane it only in plane stiffness considered by the program, and layer it doesn't deform and not having any property. So slabs are normally modeled as a thin shell, and the footings as a thick shell, right? And staircase as membrane, right? So if you have this type of members, so model them as thin, thick, and membrane. So these are manually entered. And diaphragm, one is the rigid diaphragm, and the other is the uh, semi-rigid diaphragm. If you don't assign diaphragms to your building, it will not transfer the lateral load to the building, and the earthquake will design will not be considered. So what is meshing? We divide the single element into small elements to give more accurate results, and this is the finite element method used. So meshing is done, and mass source is also used in the earthquake analysis. What we do is that we define the mass of the structure along with additional dead and live load to take into account the earthquake analysis, right? These are from the Indian standard, but the UBC and the International Building Code also has this mass source definition. And partial fixity, already explained that when you have two beams, one is the primary beam and the other secondary beam, so partial fixity option is used there, right? Otherwise, the joints are rigid, and you then give it the rigid joint connection. So I think this is for today. If you have any questions, you can kindly uh, ask. Yes, any question from anyone? You are welcome. Mass source, basically mass source is used in the earthquake analysis. If you don't give the mass source, then the building won't perform the earthquake analysis, and it will only be used as a gravitational load. Mass source, I think someone asked the question of mass source. So you kindly, you can see here, what is the mass source that we define the mass of the structure along with additional dead and live load to take into account earthquake analysis. And as per the code, seismic shell design force shall be estimated using full dead load plus some percentage of the imposed load as given in the table. For imposed load distribution, uniformly on the floor, 25% of the imposed load shall be considered when the intensity of the live load is up to 3 kilonewtons per meter square. And for imposed load distributed uniformly on the floor, 50% should be taken when it exceeds the live load of 3 kilonewtons per meter. What is meant by it? That based on the live load, you assign additional load to the structure. This is for the earthquake analysis. If you don't do it, then the earthquake behavior will not be properly established. I think this is clear now.
Is it necessary to use moment modifiers, and if not, then under what conditions should they be used?
Actually, the code gives you these factors. What happens if you don't assign, for example, the a factor of 0.35 for beam? If you don't give that, the beam will be strong enough and all the torsion will be taken by the beam. So what will happen that your design will show heavy beams, but the column will be lighter. And these are all basically strength reduction factor values. So it gives you the strength reduction and makes the building more safe.
Okay, can you shed some light on reducing the torsional moment? Sorry, torsional moment modifier. I have seen in some videos that they recommend when if the beam is not passing, you should reduce the torsional
Yes,
moment
I
modifier
will
to
explain.
0.001.
Yes,
Why
yes.
is it? Why do we do that?
1 minute, I will share the screen. Okay, I think it's visible. The torsion constant, this is used basically in beams. We can go from 1% to 10%, right? So this is a trial and error, and it should not be more than that. If it is getting more than that, So the torsion is taken by the beam, and the columns are not taking torsion. And what I explained, that beams will be strong enough and column will be weak. So 1 to 10%, normally up to 10% we take for beams.
10% is like 0.1. Yeah.
Yes, 0.01.
Yeah, 0.0. Okay. Okay.
0.1. Okay.
Okay.
Sir, shall we design a single component of a structure in ETABS?
Yes, you can design, but for why
Just
will
in
you
case,
use?
just to know the bending moment and shearing force.
Yes,
nothing
yes,
like-
yes, you can do it. You can do it.
Yeah, okay, sir. Thank you.
And now also CSI column software is introduced by ETABS CSI company. So that only designs columns.
Yeah, okay, sir.
So if no question,
I
thank
think
you very
there
much.
is no questions. Thank you very much, Zishan Saab, for taking out time and having this webinar with us. And thank you everyone for participating. And please know that this was a second webinar of our series of total of 5. So inshallah, see you in the next webinars.
Okay, take care. Allah Hafiz.
Okay.